All right, this video is going to be on solution stoichiometry. Solution stoichiometry is really like all other forms of stoichiometry. You're basically comparing the amounts, or typically we convert it to moles, of one thing in an equation to something else in the equation. The only differences in solution stoichiometry is sometimes you're not given the actual grams or liters or what have you of one thing. You're given something relating to a solution. For instance, here I have a percentage of a certain percentage of a solution. Here I have capital M, which is the molarity of a solution in a certain volume. Here I have a mass of water and a molality of solution. But I can still use these to figure out moles of one thing and then moles of another, and then from there I can get grams or liters or whatever you need. Before I do that, though, I want to review two definitions with you very briefly. Molarity, if you recall, is abbreviated with a capital M. You'll actually see that capital M used here, and molality is lowercase m. Molarity is moles per liter of solution, and molality is moles per kilogram of solvent, just the solvent. So typically for a molarity type problem like you see here, you'll be given a volume and a molarity. And again, if I know the M and I know the volume, I can simply solve for the number of moles, and then it's a stoichiometry problem like any other. Molality, similar idea. I may be given in this case a mass of solvent, so I'm given the kilograms of solvent, or grams in this case, I can convert that, and the molality, and again I can simply solve then for the number of moles and then do a regular old stoichiometry problem. So let me do a few of these and show you how to do it. You can do the whole problem through dimensional analysis, or you can just convert what you're given into moles and then feed that into the stoichiometry problems like we've done before. I'd like to show you both just to give you a feel and a comfort level with both. For instance, with this one, let's get our equation first. Sodium sulfate. Sodium is Na and sulfate is SO4. Sodiums are +1, sulfates are -2, so my correct formula here is going to be Na2SO4. This is reacting with barium nitrate. Barium is in the second column of the periodic table, an alkaline earth metal, so it's +2. Nitrates are NO3, and they are -1. Because they are -1, I'm going to need two of them to combine with that barium, so that would be your correct formula for barium nitrate. This is a double replacement reaction or double displacement reaction depending on the phrasing, but this will only occur if one of the products is soluble, or insoluble I should say, and NaNO3 is going to be one of my products. That is soluble. All your nitrates are soluble. The barium sulfate will be my precipitate. That will be the insoluble thing. So let me write my formula here. NaNO3. Again, sodiums are +1, nitrates are -1, so I just have one of each. BaSO4, and I'm going to do, that's my precipitate. I could do that. You could do an S back there too, just to let somebody know it's a solid. But again, this is precipitating out of solution, and bariums are +2, sulfates are -2. To balance this, let me see here, I would need a 2 here, and then I think I'm in good shape. So that's really all you need to do to balance it. Now, the question is how much precipitate will form, so I'm trying to find the barium sulfate, but what's happening is they're not giving me the actual grams or anything like that here. They're giving me the percentage, so I'm going to have to get that and solve the problem. So let me do it separately first, and then I'll show you the whole dimensional analysis. In this case, what we would do is I have 15.6% of 25 grams is my sodium sulfate. So what I could do here is do 15.6 is 0.156 times 25.0, and if you figure that out, that means you're going to be starting this reaction with, I believe if I did my math right here, kind of doing this on the side here, 3.9 grams of the sodium sulfate. So now that I know that, I can very easily then go from, and actually, you know what, let me do my labeling here. Grams of Na2SO4, and then I would go from grams of Na2SO4 to moles of Na2SO4. This is always basically a conversion. I'm going to divide by the molar mass, so I have a 1 there. And the molar mass, I figured this out earlier, I believe it's 142.1. And then I'm going to go from moles of Na2SO4 to moles of, in this case, BaSO4. And again, here you use your molar relationship. So there's nothing there, so that's a 1. Na2SO4, that is also a 1. And then from here, I can go from, they want to know grams. So I'm going to go from moles of BaSO4 to grams of BaSO4. And for that, again, there's going to be a 1 here, and now I'm multiplying by the molar mass, and I also figured this out earlier, and I believe I have 233.4 grams. So now if I do all this calculation here for an answer, I got 6.41 grams of Ba. That looks like a D there. Let me clean that up. BaSO4. So I have that then as my correct answer. Now, what I did again a minute ago is I just basically took the percent in decimal form times my mass, and I got my problem there. If you wanted to start and do the whole thing in a dimensional analysis, what you would actually do is start with what's given, and I would start with 25.0 grams of Na2SO4, and again I would times that by grams of Na2SO4, and then my amount of Na2SO4 is going to be, what's the percentage here? It was 15.6, so that would be 15.6 grams of every 100 grams is going to be my solution. And just to be clear, let me rephrase this a little bit. This is 25 grams of the solution, and this is the solution as well. So what's happening is, because it's 15.6% sodium sulfate, 15.6 grams of every 100 grams of solution is sodium sulfate. So if I have this much solution and 15.6 grams of every 100 grams, because this is the percent, this is per 100, of 15.6 grams of every 100 grams of solution is my solid. This, if you multiply this out here, notice that's the same thing I really did here. 15.6 over 100 is 0.156 times 25. That gives you 3.9. So this and this are basically synonymous. What I did here is I just did the conversion to get moles, and then, or grams I should say, and then I fed it right into my molar conversion, whereas here I set it up so that I had grams of solution, and then I went from grams of solution to grams of solid, and then everything else would be the same. So then what would happen is I would do times, and then this would go here, this would go here, this would go here, and then I'd get the exact same answer. So that's how you do the whole thing in one long dimensional analysis or factor label problem. Let's look at the next one. Same sort of idea. Here I'm, instead of being given the moles, again I'm given the molarity and I'm given the volume. So again, if you wanted to do this as a separate problem, like you wanted to break it up, what you would end up doing is, and let me do a little of this over on the side so we have some room, but what I would do here, and actually let me do a different color for this problem as well. I'll do this one in red. But what would happen here is, if you remember that molarity is equal to moles per liter of solution, if you'll notice in my problem, my liters here, 25 milliliters is 0.025 liters, so I have that. My molarity is given to me as 0.100. So if I want to solve for the moles, you would multiply, this is in the denominator, so you multiply both sides by 0.025. So times 0.025, this cancels, 0.025, this would cancel. And if you do all that, you're going to get 0.0025 moles. And then once I know the amount that I start with, the amount I'm beginning with, then it becomes just, again, a plain old stoichiometry problem. So let me write that out, and I'll kind of do this in a similar fashion as last time. So I would start with, what do I get here? 0.0025, and this is moles of sulfuric acid, so this is of H2SO4, times in a line, and I'm going to go from moles of H2SO4 to moles of, what do they want? They want the hydrogen gas, so that's this guy, H2. And now again, my molar bridge, I use the coefficients from the balanced equation, and I have a 3 here, and I have a 3 here actually, so it's a 1-to-1 relationship. And now I'm going to go from moles of H2 to, they want molecules of hydrogen gas. So I use MC here of hydrogen gas. And if you remember, the number of molecules is 6.02, the number of anything, atoms, molecules, whatever, 6.02 times 10 to the 23rd molecules per mole. So again, I would just do my math here, and let me see here, that's going to be, I think, 1.51 times 10 to the 21st molecules of hydrogen gas. Okay, so again, what I did is I got the number of moles by using my stoichiometry. Now, again, if you wanted to do this, I did this part on the side, then fed this into the problem. If you wanted to do this as one big problem, you could actually start with 0.025 liters. That's what they give me. I'm starting with 0.025 liters, and then times, and I'm going from liters to moles. Well, what is moles per liter? Moles per liter, if you notice, that is my molarity. So it's basically 0.100 moles per 1 liter. And again, if you multiply that out, you're going to get 0.0025, which is exactly what I did here. And then the rest of the problem is the same. And of course, my solution would be the same as well. And now for this last one, it's the same idea. It is in molality, though, so slightly different. And let's, I don't know, just mix up the colors here. Let's go with green on this one. In this case, let's see, enough PbNO3 is added to water. Okay, so we've got a solution, and then I am reacting NaI with that, and I'm producing lead-2 iodide. Okay, so to get my equation, let me first of all start with that. I'm going to react lead nitrate, PbNO3 that's actually given to me. PbNO3 is reacting with NaI, because that's my other reactant here. It's added in excess, so we know we have plenty of that. There's no limiting reactant issue here. This is going to be a double replacement reaction. Let me do the one I know soluble first. We know nitrates are soluble, so that's going to be NaNO3. And then, of course, my other material is going to be the lead iodide, because this is a double replacement, so the lead will join with this. And the lead has a +2 charge here, so I'm going to make this PbI2, and that will be my solid. I did a down arrow up here in the first reaction. I'll do a solid there, but it's basically the same idea. And now in terms of balancing, let's see here. I need a 2 iodine, so I'll put a 2 here. Which means I need a 2 there, and I think I'm okay. So now I have a balanced equation. Now to figure out the amount of material to start with, again, I'm going to go back to my equation here, that molality is equal to moles per kilogram of solvent. They give me, again in the problem, they give me the molality as 1.50 molal, and they give me the amount of solvent as 450 grams, that would be 0.450 kilograms. So now again, I multiply both sides by 0.450. Let me see, what do you get here? 0.5. I believe, if I'm doing this right here, you're going to get 0.65. I'm doing this over on the side. So you're going to have 0.675 moles of, what am I starting with here? This is my PbNO3, my lead nitrate. PbNO3. Okay, so this is what I'm starting with. So now we go back to the stoichiometry. I have a certain amount of this, and they want to know how much of this is coming out. Well, this ends up being a rather easy problem. I'm going to squeeze this over here on the side because it's a one-to-one relationship, and they don't even want grams. All they want is the moles of lead-2 iodide. So what I'm going to end up with here is 0.675 moles of PbNO3, and they want, I'm going to go from moles of PbNO3 to moles of, they want PbI2, and again, that's 1-to-1, which makes it super easy, because then my answer, of course, is 0.675 moles of PbI2, because stoichiometry tells me that for every 1 mole of this, I'm going to produce 1 mole of this, because it's a 1-to-1 relationship. And again, I could have also done this in the equation. Rather than having the 0.675 here, I could have very easily just started with the what'd they give me here? 0.450 kilograms of my solution, and then gone times in a line, and then basically for every kilogram of solution, I have 1.50 moles of my material. So again, this would give me this, and again, and then I would just basically multiply by 1/1, and you would get the same 0.675 as your final answer. So that's solution stoichiometry. It really is no different than the other stoichiometry we've done. It's just you have to determine the number of moles you're beginning with in a different format.